Today we're going to be covering the units on geometric optics. The first topic we introduce in this unit is the topic of reflection. We have different types of reflection, two different types. You have specular, that is interesting, specular reflection, and you have diffuse reflection. Pretty simple difference. Specular reflection means that light rays come in and they are reflected back in a straight line. Okay, specular reflection is characteristic of flat, smooth, uniform surfaces. Okay, a light ray comes in, and this is how we're going to be illustrating light rays in Physics 2, where it's going to be illustrated as a line or as an arrow. Okay, light ray comes in and it diffuses back out in a straight line, and then the light ray comes in and it diffuses back out exactly the same as the first one, and so on and so forth. All the light rays that come in diffuse out or reflect out in exactly the same way. Okay? Diffuse reflection, on the other hand, is characteristic of bumpy, non-uniform surfaces. Okay, so a surface that is not flat. You get the idea. Okay, a light ray might come in and it might get reflected out this way. A light ray might come in, get reflected out that way. Come in, reflected out that way. You see that the light rays are not consistent in the direction in which they are being reflected out. Okay? This is specular reflection, is reflection that produces coherent light, and diffuse reflection scatters light. So what's an example of diffuse reflection? Painted white wall around my whiteboard, that exhibits diffuse reflection. How do we know it exhibits diffuse reflection? Because in diffuse reflection, you can't see your reflection. That's the characteristic of it. In specular reflection, you can see your reflection. In diffuse reflection, you can't see your reflection. So let's move on from there, a pretty simple topic to understand, to the topic of refraction. What is refraction? Refraction is that whenever we have a surface, we are going to, for the remainder of the unit, assume specular reflection, because that's what the rest of the unit deals on, specular surfaces. If we have an incident light on a specular surface, some of that light will be reflected, but some of that light will be refracted. This is the reflection component that we just talked about. This is the refraction component. So let's get more into that, okay? Let's pretend that this surface right here is a block of glass. All right. Whenever we shine light on a block of glass, some of the light will be reflected back at us. That's why when you walk up to, let's say, a bike store showroom window, when you walk up to the window on the side of the store, you can kind of see your reflection in the window, but you can also see through the window. Okay? That's what this process is describing for us. Some light is reflected back, some light is refracted through. So refraction is the occurrence of when light travels from one medium to another, okay? So keep in mind out here, as the light is traveling through air, and then at this interface, the light transitions from air to, in this case, glass, okay? As the light ray transitions between different mediums, the speed or the velocity of the light ray will change. As we might assume, it is easier to travel through air than it is to travel through glass, okay? So in this particular example, it would be harder for light to travel through glass. Therefore, the speed of light will decrease as it travels through the glass relative to the air, okay? We often know the speed of light as a constant. It is a constant, but that constant defines the speed of light in a perfect vacuum, okay? The speed of light in a perfect vacuum will never change. However, we can change the medium or material through which light is traveling. Therefore, we can change the speed of light in that medium. Okay, speed of light given on the first page of your reference table is given by the constant c, which is 3.0 times 10 to the 8th meters per second. Okay, so when we talk about refraction, we identify that each material or each medium through which light travels is identified using an index of refraction. Your reference table uses n, the letter n, to represent the quantity for index of refraction. And on your reference table, you are given the equation that n equals c over v. That says that the index of refraction of a material is equal to the speed of light in a vacuum divided by the speed of light in that material. Therefore, as the index of refraction of the material increases, the velocity of light in the material decreases. Let's examine here. When n equals 1, you are looking at c over c, or that the speed of light in the given material is exactly the same as the speed of light in a vacuum. This is approximately the case for air. Okay? The index of refraction for air is approximately 1. Once you're given index of refraction, we need to understand how the light curves when it is refracted. If you'll notice here, refraction makes some angle theta with the vertical. Yes, we're dealing with a vertical line here, such that if the index of refraction of medium 1 does not equal the index of refraction of medium 2, that means that the angle theta 1 that the incident ray makes with the vertical does not equal the angle theta 2 that the excident ray makes with the vertical. So that introduces a whole new analysis of how we determine the geometry of how different rays interact at this point, okay? So first of all is our law governing reflection. Make sure you don't get confused between reflection and refraction. Reflection and refraction. The law of reflection states that any incident ray onto the medium produces an excident ray such that the theta 1 that the incident ray makes with the vertical is exactly equal to theta 2 that the excident ray makes with the vertical, such that theta 1 equals theta 2. And that is a hard set rule. The law for refraction, refraction being the portion of the light that passed through, if we draw our medium and we draw our vertical, an incident light as such will bend towards or away from the vertical, okay, such that the angle that the incident makes with theta 1 and the angle that the excident makes with the vertical, theta 2, is related by this equation, such that n1, being the index of refraction of medium 1 up here, times sine of theta 1 equals n2 times sine theta 2. This equation is known as Snell's law, where medium 1 is on this side of the boundary, medium 2 is on this side of the boundary. If we return to this example, medium 1 would be our air, medium 2 would be our glass, okay? So, in all of your physics problems, if you are asked to do Snell's law, for example, very often you would just be outright given theta 1, and you'd be given n1 and n2, and you'd be asked to solve for theta 2, which was very straightforward. You'd be asked to plug and play. So the index of refraction of air, as I've already discussed, is about 1, and the index of refraction of glass is about 1.51. Okay, so we can see that the index of refraction increases as the light travels across the border. Okay, and qualitatively speaking, going from a lower to a higher index of refraction pulls the light closer to the vertical. Going from a higher index of refraction to a lower index of refraction causes the ray of light to be pulled away from the vertical relative to the incident ray. So, given that in the example of going from high to low, your theta on the outside will always be greater than your theta on the inside, we can introduce a topic known as total internal reflection. Okay? Total internal reflection is a process or an occurrence that can happen when a light ray is going from a medium with a high index of refraction to a medium with a low index of refraction. So let's illustrate that right now. Let's say I have a medium up on the top, which is air. let's call that medium 1, and a medium on the bottom, well, let's say it has an index of refraction of 3, all right, which is pretty high in this case. So if I have an incident ray that comes in like this and makes an angle theta 2 with the vertical, then it'll create a excident ray that diverges away from the vertical because we're going from high to low, okay? So I can continue to move this incident ray further out. I can increase theta 2, and therefore that will further increase theta 1 until theta 1 is 90 degrees, okay? And if I keep increasing past that point, if I keep increasing theta 2 until it's all the way out here, then theta 1 will have increased so much that it is now on the other side of the medium, okay? Now theta 1 is so big that the refracted ray no longer leaves the original medium. Theta 1 is so big that the light ray is completely reflected internally in the medium. Thus, total internal reflection, okay? So we can try and identify at what angle theta 2 do I need in order to cause total internal reflection, okay? So let's start back up with Snell's law. Let's write it out. And let's say, what conditions in Snell's law quantify a total internal reflection? Total internal reflection starts to happen when the excident light ray no longer leaves the original medium. And that happens the moment theta 1 turns to 90 degrees, okay? So we can set theta 1 equal to 90 degrees. Now what's sine of 90 degrees? Sine of 90 degrees is 1. So therefore we can rewrite this equation as n1 equals n2 sine theta 2, and this is our condition for total internal reflection, okay? So if we want to particularly solve for theta 2, if we want to particularly know the angle theta 2 at which total internal reflection occurs, we can do that. We can say, we can rewrite this as n1 over n2 equals sine theta 2, which can then be rewritten as theta 2 equals the sine inverse of n1 over n2 as such. Okay, that is our condition to solve for the angle at which total internal reflection occurs. Okay, and again, it can only occur when we're going from medium of high index of refraction to medium of low index of refraction. All right. Let's say that the high index of refraction was on top, then we would be looking for theta 1. And again, if we're going from high index of refraction to low with the high index of refraction on top, this would instead be n2 over n1. So make sure to rederive your equation accordingly. Okay? Moving on from there, we are going to deal with mirrors. And mirrors deal virtually exclusively in reflection, okay? So let's take an example of a mirror. And I hope you guys are all following along with your equation sheets in hand, because I want you to familiarize yourself with where all these equations are coming from as we do these. Let's go on to mirrors, but before we do that, there is an equation, the very first equation you see on your reference table is the equation that lambda equals c over f, okay? What does that equation mean? Lambda is the wavelength of your light wave. Frequency, f is the frequency of your light wave, all right? And you hear me saying light wave because light is treated as a wave in this unit. We're going to get much deeper into the sort of paradoxical wave-particle duality of light. That's going to be next unit. But for right now in this unit, we're going to treat light as if it were a wave. Okay? If I were to draw a sinusoidal wave, which light is, as such, the wavelength of the wave is simply the distance between two of the same illustration in a wave. So the distance between two troughs, the distance between two peaks, the distance between two descending zero values, those could all be used to calculate your wavelength. It is the time is the distance between two repeating instances in a wave. Okay? So this states that your wavelength is equal to your constant c, the speed of light, divided by the frequency of the wave. Frequency just states how many times does a wave pass a certain point. Okay, so a frequency is in units of seconds to the -1, or 1 over seconds. This unit is known as hertz. That's why you hear frequencies in megahertz, gigahertz, etc. Now, with all that being said, let's get back to mirrors. Okay? So we're going to be dealing with two types of mirrors, those being convex and the concave mirror. Okay? And they're going to be parabolic mirrors, and you'll see why in just a moment. I'm going to have my floor here, and my object is going to be represented with an arrow pointing upwards, signifying that the object is upright. Okay? So I'm going to draw my curved mirror right here. Okay? And in a curved mirror, it's going to look like a circle. And since it's a circle, all circles have a center point. So let's say that the center point of our circle is right about here. That's our center point. Okay? All mirrors and lenses have what is called a focus, or a focal point. In the case of mirrors shaped like this, the focus is always half the distance of the center. So in this case, our focus would be right here, exactly halfway between the center and the edge of the mirror. Okay? So now we can answer the question of what kind of image is going to be created when I place this object in front of this mirror. Okay? And that involves a process called Raytracing. Now, in Raytracing, there are three types of rays, light rays, that will help you determine the image that is produced by such a mirror. Okay? So the first ray that you need to do is a ray from the top of your object goes exactly parallel to the floor and hits the mirror. Okay? All light rays that are exactly parallel to the floor will reflect off the mirror and go through the focus. Okay, as such. That is how the mirror reflects those kinds of light rays. Every light ray that hits the mirror directly in the center is reflected back as if it were perfect reflection, meaning that the angle theta that you make with the horizontal is exactly the angle theta that the returning wave will make with the returning ray will make with the horizontal. That's a little too far out. Let me remake that like that. Yeah, that looks better. And the third type of line or light ray that we need to concern ourselves with here is that all rays that go through the focus of the mirror are returned by the mirror exactly parallel to the horizontal. Okay? So given those three rays that we have just made, they all three should intersect at a certain point. Okay? The reason that I like to use 3 and a lot of other people like to use 2 is that this was a really hard topic for me to understand. So I would often just use 2 like everyone else told me to do, and I would end up messing up something. Like, I would call this the intersection point by mistake, which was the wrong one. And it would be very easy to make that sort of mistake. I might call the focus the intersection point, which was obviously wrong. And it's a lot more reassuring to have 3 rays so that you're sure that the intersection point of all 3 rays is absolutely your correct intersection point, okay? Because if you do one of the 2 rays wrong, and you do your 3rd ray and you realize they don't all intersect somewhere, you at least have the confirmation that you did something wrong. So a lot of kids told me that they learned it with 2. I say always do it with 3, because it's really, really easy to make a mistake when you're drawing these lines, okay? They allow you a ruler on the Physics 2 exam. This is where you're going to want to take advantage of it, because they usually have these as FRQs. Okay, anyway, back to my intersection point. Why am I talking about an intersection point? Because the intersection point is where your image is going to end up. Okay, the mirror produces an image. So to draw my image, I start on the horizontal and I draw a line to my intersection point and I give it its arrowhead like that. Okay, such that this was my original object and now this arrow is my image. You'll notice that the image is inverted, meaning it's upside down, and the image is real. Okay, what do you mean it's real, Meek? What does that mean? A real image forms on the same side of the mirror as the original object, and a real image has a positive distance from the mirror. And we're going to cover the equations in which that's going to make sense. Also, a real image is formed by real converging light rays, not traced back light rays. And we'll cover what exactly that means right now, okay? So in order to cover the difference between real light rays and traced or imaginary light rays, we need to consider the example of the diverging mirror. As such, if I draw my horizontal, we can draw the diverging mirror, which curves outward like this, okay? And since it curves in a different direction, its center will be on the opposite end of the mirror, and its focus will be on the opposite end of the mirror, okay? So this is what I was talking about before. A negative distance, in this case, is a distance on the opposite end of the mirror. A negative focal length is a focal length that is on the opposite end of the mirror. I don't think I explained that yet. This is the focal length, the distance from the mirror to the focus, okay? A negative object location means an object is on the opposite end of the mirror, or a negative image location, I should say. So let me draw my image, and let's understand how this mirror works. So again, the mirror side is the side facing our object. So a incident ray that goes into the mirror is going to be reflected back outwards like this, okay? So if I were to do the first ray, and I were to draw a ray horizontal, exactly parallel to the floor, then that ray would be reflected back out like this. However, we discussed here that all rays that are horizontal or parallel to the horizontal will go through the focus. So we have an imaginary line that goes through the focus, and we will extend that line outward to represent the actual direction in which the ray is reflected, okay? We also discussed that a ray that hits exactly in the center of the mirror will be reflected back as though it were reflecting normally, as such. And we can draw the imaginary component of this reflected line, as if it were reflecting normally on the horizontal, okay? And then we say that all lines that go through the focus will be reflected back horizontally, okay? This line is going to go through the angle is a bit off here. This line is going to go through the focus. It's going to have an imaginary part that continues on horizontally and the real part is reflected back this way horizontally, okay? So we notice that the real parts of all of our reflected rays never touch, but the imaginary parts have an intersection on this end of the mirror, and that's where we're going to draw our image. That's where our image is going to appear, okay? So in this case, our image is upright. Our image is smaller than the original object. In this case, the image was also smaller than the original object. But here, our image was imaginary. Okay, the telltale signs of being an imaginary image are that the image is a negative distance, and a negative distance means that the object, or excuse me, the image is on the opposite side of the mirror relative to the object. Okay, but the be-all, end-all rule for whether an image is imaginary or real is all real images are formed by the convergence of real rays. All imaginary images are formed by the convergence of imaginary rays, or backtraced rays, as some people call them. Okay, so from there, we can delve back into our equation sheet to exemplify one of the equations we are given, such that 1 over SO plus 1 over SI equals 1 over F. All right, so what is that telling us? This is 1 over the distance to the object plus 1 over the distance to the image equals 1 over the focal length. O for object, I for image. Okay. So it's another 3-participant equation, and you would be given that the object is placed 25 centimeters away from the mirror. The mirror has a focal length of, let's say, 10 centimeters. And the problem would also tell you this is a converging mirror, which is this type of mirror, or it's a diverging mirror, which is this type of mirror. It could also tell you that it is a concave mirror, which is this type of mirror, or it's a convex mirror, which is this type of mirror. The easy way to remember that is concave forms a cave, forms a depression. Okay? If you are looking at it as the image, if you're looking at it as the object, then the mirror looks like a cave, like a recession. Okay? So if it says that the focal length of the mirror is 10 centimeters, and it also tells you that we're dealing with a diverging mirror, then the focal length is negative 10 centimeters. So that is important when we consider this equation. We just say that 1 over 0.25, because these are all going to be in units of meters, plus 1 over the distance to the image equals a negative 1 over 0.1. And from there, we plug things into our calculator. 1 over 0.25 is 4, plus 1 over the distance to the image equals negative 10, because 1 over 0.1. So now we can subtract 4 from both sides. 1 over SI equals negative 14. And we can rewrite this, I'm going to rewrite it over here, that 1 over negative 14 equals the distance to our image, and that into the calculator becomes negative 0.07, which is the same as 7 centimeters on the right side of the mirror, okay? Which makes perfect sense. We are dealing with a negative focal length, which indicates we are dealing with a convex mirror. So our focal length should be negative because a convex mirror creates an imaginary image on the opposite side of the mirror. Let's try and show how ray diagrams are constructed for convex lenses and concave lenses. Okay, convex lenses, positive focal length, means where is our focus? Focus is going to be on this side. Okay. However, a lens is different from a mirror in that you have a focus on both sides. of the lens. Okay? And that's why it's confusing that even though the lens has two foci, the focal length for a convex lens is positive and the focal length for a concave lens is negative. Okay, so let's draw the ray diagram for the convex lens. A ray comes in like this, goes to the center of the lens, and again, remember our three rules. Horizontal rays that are parallel to the horizontal diverge through the focus. A ray that goes through the exact center of the lens, since this isn't a mirror, the ray is not reflected. It continues on completely unchanged. Okay? And all rays that go through the focus, you can like draw out your mirror a little bit here. All rays that go through the focus, sorry, I said mirror, I meant to say lens. All rays that go through the focus are diverged exactly horizontal once they encounter the center. There are real light rays converging on this point right here. That's our intersection point. That's why a convex lens is often denoted as a converging lens. So this is going to be our image here on the right side. So let me ask you guys, is this an imaginary image or is it a real image? It's a real image because it's made by real lines. Now let's move on to this guy. Concave, also known as diverging lens, has ray diagrams that looks like this. All horizontal rays come, they contact the center of the lens, and they diverge outward. But they diverge outward such that the backtrack intersects with this focus. All rays that encounter the center of the lens proceed through unchanged.
So Meek's about to make a mistake here. I cut it out, but what I should have done is I should have drawn the third ray going through the focus on the right side of the mirror. That's what you do when you draw lens diagrams, is one ray trace goes through one focus, another ray trace goes through the other focus. So here's the correct diagram.
So again, the mirror equation, 1 over SO plus 1 over SI equals 1 over F. The equation still holds true for all lenses, but you've already seen that demonstrated. Another equation that holds true for both mirrors and lenses is the magnification equation, such that the magnitude of your magnification is equal to, let me find my reference table again, is equal to the magnitude of the height of the image divided by the height of the object, which is equal to the distance to the image divided by the distance to the object. Let's say that the height of this image is 10 centimeters. I'm sorry, the height of the object is 10 centimeters, then the height of the image is 12 centimeters. And let's also say that the distance from the object to the lens is 8 centimeters. So given these, we're going to use the magnification equation to help us determine both the magnification and the distance to our image, So we can say the magnification equals height of image, 0.12 meters. In this case, the height of our image would be a negative 0.12 meters because the image is underneath the horizontal. Okay, height of our object would be 10 centimeters, and that is equal to the height of our image, not the height of our image, the distance to our image, which we don't know, we're still trying to find out, divided by the distance to our object, which would be 0.08, 8 centimeters. Okay? So we know the magnitude of 0.12 over 0.10 is 5/6. So our magnification is 6 over 5. And that's also equal to SI over 0.08. 0.08 is 4 over 50. because 0.8 is 4 over 5. So magnitude equals 6 over 5. Magnitude times 0.08 equals the distance to our image. So the distance to our image is equal to 6 over 5 times 4 over 50 equals 24 over 250, and that is the same as 96 over 1000, or 9.6 centimeters, which makes sense. Our image is slightly further than our object, so the distance should be slightly further than the object. Okay, that is the entirety of this unit. Thanks for watching, guys.